So next and finally, we will hear from Alice Schwarze from the University of Washington. And the title of her talk is Motifs for Processes on Networks. And so Alice, whenever you are ready, please take it away. Looks good. Here we go. Oh.
Okay. Do you see the title screen?
Yep, we can see it.
Awesome.
Here we go.
Thank you. So I would like to talk about motifs for processes on networks. This is more of a theoretical work, but it is helpful, I hope, to uncovering the principles that Stefan mentioned in the end that connect dynamics and structure in networks. So I'll start with a one-slide summary. And like Stefan, I'm interested in network structure in the brain and physical processes that can happen on that structure and how that relates to questions of neural coding. So I'm taking a motif-based approach, which means that I focus on how small parts of a network structure influence microprocesses on networks and how these microprocesses in turn are associated with small changes in information theoretic measures. And this is, of course, work that builds on previous work by lots of great people. There's quite a few excellent papers on connecting mathematical models of brain dynamics to information theoretic measures that are used in neural coding. Connecting these mathematical models to structural connectivity is essentially a combinatorial problem, and that's part of the aspects that Mason and I hope to bring to the discussion with our paper. So before I move on, I want to talk briefly about what I think this is good for. Connecting motifs in models of physical processes to information theoretic measures can give us a physical interpretation of the abstract measures that we use, for example, in IIT. And secondly, by making the connection between structure and information, we can get another way to go about understanding the relationship between structural and functional connectivity. So, and here's the pipeline for the rest of the talk. Well, I'll start with the pipeline for the framework that Mason and I are proposing, and then I'll give a brief example using just covariance and correlation for the Ornstein Uhlenbeck process. And so here comes the pipeline. As I said before, our starting point is that we choose a mathematical model of a dynamical system for neurodynamics, and this could in principle be something like an integrated fire model. In practice, it makes sense to choose a model that is as simple as possible, and that's why we're going with the Ornstein Uhlenbeck process in a minute. Then we choose a system property, which I call Y, and again, Y in principle can be anything. In practice, we need to be able to obtain a matrix power series expression for Y, and that's not always easy, but it definitely works when we choose Y to be correlation, covariance, mutual information, and entropy for the Ornstein Uhlenbeck process. Next, we interpret the matrix power series as contributions of microprocesses to Y. And this has something to do with the fact that one can interpret elements of powers of adjacency matrices or connectivity matrices as weighted sums of all walks that connect one node in a network to another. And counting the microprocesses that can occur on a small piece of network structure, we can infer the contribution of a structure motif to Y and from the contributions of microprocesses that happen on it. And finally, using these contributions of structure motifs, we can learn how network structure can enhance or reduce information theoretic measures in a network system and get something like a ranking of motifs and how much they contribute. So let's start with the example. We have the Ornstein Uhlenbeck process, and we're looking at covariance and correlation in that simple system. Many of you probably already know the Ornstein Uhlenbeck process and have worked with it yourself. It's a noisy mean reverting process, meaning that when you poke the system, like I've done here and here in 2 time points, it noisily returns to its mean value, which in this case is 0. A nice feature of the Ornstein Uhlenbeck process is that one can derive its steady state covariance matrix, which I call sigma, in a very nice form. You see here that sigma is a matrix power series of the adjacency matrix. And this equation tells us that you can get the covariance matrix just by summing over two indices. So we have here uppercase L and lowercase l. And each of these terms corresponds to one summation of some product of matrices. So we can get a similar expression also for the correlation matrix. That one comes out to be a little bit longer, and you have to kind of be aware of more summation indices, but essentially the idea is still the same. So in this, now we're at step 2, right? So we have the matrix power series that we wanted. And before I move on, I want to talk about why this is important. So a graph theory fun fact is that powers of adjacency matrices tell us something about the number of ways that a signal can walk from one point in a network to another. So for example, when we have, when all connections have the same strength, then the ijth element of the, say, fifth power of the adjacency matrix tells us something about the ways that a signal can travel from the node J to the node I. And the fifth power of A transpose tells us something about how a signal can travel from the node I to the node J. And if we have a term like this that consists of A and A transpose, then what that refers to is that somewhere we have a source node, and from that source node, in some specified number of steps, we can walk to node I and to node J. And for the rest of the talk, I draw these out as these kind of walk diagrams with numbers on blue edges indicating walks. And this brings us to the third stage of the pipeline, where we look at the matrix power series that we derived in stage 2, and we find the process motifs that are associated with the summons in the matrix power series. And for the covariance power series, we have seen on the previous slide the associated microprocesses, and they look like this. So here we have the process motifs for covariance, variance, and correlation. And what I like about these results is how intuitive they are. So we see that the process motif for covariance between the nodes I and J, those are microprocesses where a signal can move from a source to both I and J, or just from I to J, which we get when we set this parameter to 0, or from J to I, when uppercase L minus lowercase l is 0. So what this tells us is something that we already know. When we have covariance, statistical dependence between the nodes I and J, it either indicates that there's a causal relationship from I to J, from J to I, or that there's a third variable that causally influences both I and J. So similarly, we get the process motifs for variance from the diagonal elements of the covariance matrix. And in that case, the nodes I and J are the same nodes, so the process motifs look like this. And for correlation, they look a bit more complicated, but they are actually just made up of one process motif for covariance that connects the nodes I and J, and then several process motifs for variance, both at the nodes I and J. And this also makes sense because correlation is essentially covariance normalized for the variance at each node. So now we get to the part where we connect process motifs to network structure. And the main idea is to enumerate all process motifs that can happen on a small structure. And when we do that, we get a ranking of the small subgraphs and how much they contribute to covariance and correlation. And the results, they can look like this. But actually, this slide is really just me flexing that I can compute these small motif rankings. The ones that are actually insightful are the small ones, so where we have just one or two edges in the system. And so these are just all possible structure motifs with one or two edges that can contribute to covariance and correlations. The blue ones have a positive contributions, the red ones have a negative, and the white ones have a 0 contribution. Now, unsurprisingly, a single directed edge from the node J to the node I, or vice versa, as we see here in this panel A, has a positive contribution to correlation. But there are structure motifs that have a negative contribution to correlation, and these tell some interesting stories. So we're taking panel J over here. It tells us something. It tells us if we have a network structure in which J sends a signal to I, which we already know from panel A that it has a positive contribution. But if we then add more in edges to I, that decreases the correlation between I and J. And this is again intuitive because from J's point of view, it sends a signal to I, but what arrives at I gets perturbed by kind of noise from other sources. Another maybe less intuitive and more surprising example is when we look at panel K. So we already know that sending a signal from J to I has a positive contribution to correlation. but then adding another edge in the other direction. So we're going both from I to J and from J to I has an added negative contribution. And this has something to do that this kind of echo chamber effect actually increases the variance in both nodes, and therefore net has a negative effect on the correlation between the two. So to conclude, I'll go back to the slide from the beginning. We use the Ornstein Uhlenbeck process as a simple approximation of physical processes that might occur on a network of neurons, and we derive process motifs and structure motifs that contribute to covariance and correlation in this model. And in doing so, we found a lot of results that either confirm or extend intuition on the relationship between covariance, correlation, and network structure. I hope to have convinced you that it's possible to obtain physical interpretations for information theoretic measures from a combination of dynamical systems and graph theory ideas. And this approach gives a clear and quantitative link between network structure and information theoretic measures. In particular, we can get a mechanistic understanding of how network structure can enhance and reduce information theoretic measures. And in terms of future work, I'm currently working on getting the process motifs for entropy, which kind of look like this, but there's like a few more details to hack out, and mutual information. And in principle, we can look at other information theoretic measures too. Here I rely on people who are more versed in neuroscience than I to tell me what is interesting here. And I also expect that the process motifs can be helpful for improving methods for network inference. And so if any of this sparks your interest, feel free to look at our preprint or get in touch with me. And that's it from me. Thank you.
Fabulous. Thank you so much, Alice. This was really interesting. And so if you enjoyed the talk, please drop some praise in the chat. So we have time for just a few questions here. We have first some questions from the panelists, actually. So the first question is from Stefan, and I'm not sure whether you just want to ask this yourself or whether I should read it. Please go ahead.
I can easily ask it. I just think that this is absolutely fantastic work, Alice, and linking structure to activity is important. But personally, I think that the main task of a brain is to compute. Do you think, can you speculate on how these types of tasks can be, these types of models can be applied to computations?
I think it helps indirectly with that. So my main idea was to look at things that people use to characterize activity in the brain. And there's a lot of that going on using information theoretic measures. And so my ambition was to get a better understanding of what these measures measure in terms of structure, and thereby understanding how, as Emcee put it earlier, how structure can constrain what we're actually going to see in terms of dynamics. So these small graphs that I had on my slides, they don't tell you anything directly about what kind of computations are going to happen. But if you believe that information theoretic measures can tell you that, then this is a way to link those back to structure and thereby make a link between computation and structure.
Great. So it looks like we have time for just one more quick question. So in 2 words, actually, let's do 2 questions. Emcee from the panel is also asking, how difficult to compute higher order motifs? Very, not very?
Not very. So the results that I showed today, the stuff that I looked at in the end, those were for 1 or 2 edges, right? And so that corresponds to kind of first and second order in the matrix power series. But going to higher order is really just keeping more of the terms, and that's what I had on the previous slide. So it's possible. It becomes harder to interpret what you see, because you saw already that there's like a rich kind of thinking of, oh, if I have 2 edges and it's negative, how am I supposed to interpret that? And as you have more and more in there, it gets a bit nitty-gritty. But like the computation is not the bottleneck. The making sense of it then becomes the challenge. So if you're into doing something like that, I can always use help in interpreting what the computer spits out.
Fantastic.
Thank you.
And very, very briefly, because we are just about out of time here, Anatoly Bushin is asking in the Q&A, is it possible to compare your theory with the graphs observed in neural systems, C. elegans, connectome, EM data, etc.?
I think it should be. I haven't done that, but looking at how this relates to actually measured network structure is something that I'm really interested in. Stefan knows that I am, so I've been looking to work with actual data sets and do some comparison on the mathematical models and what we find in the data. So yes, definitely.
Fantastic. And I think we're just about out of time, but very quickly, Rainier Engelkind is asking, great talk. Can you comment on how you think these results would change in nonlinear networks in 30 seconds?
30 seconds, nonlinear networks. Okay, so this was for a linear system, as you've correctly pointed out. If you move to a nonlinear system, you can't really interpret things that you see as the sum of small parts, because that's what nonlinearity does to it, right? So what you can do in a nonlinear system is you can linearize around a point that you find interesting, like a steady state or something, and then do the same stuff that I did. If you want to be really in a nonlinear regime and want answers that apply to all of your state space, this is not going to help you. But I think generally a motif-based approach won't be applicable to that, because again, you can't, in a truly nonlinear case, you cannot take something and divide it into parts and say, I know what each of those parts contributed.
Well, that seems like a good note to end on. So thank you.